reaching me out and providing this platform to share our work. So to disclaimer, right? So while my background is not specifically in AI or machine learning, I'm very excited about the potential that machine learning and AI offer in advancing our understanding of microclimate and developing more effective strategies for sustainable urban environment. So I believe that by interacting with and learning from experts like from this community, we can explore innovative ways to integrate AI into our research and thereby enhancing our collective impact on climate action. So for today, I'll be sharing some insights from our work of the CoolNUS-BEAM initiative, where we have been collaborating with various researchers to assess and improve the microclimate within our campus. So I look forward to your feedback, suggestions, and any ideas that you might have on how AI can further elevate this work. Okay, so I'm originally from Jakarta, Indonesia. I moved to Singapore in 2007 to pursue my studies and have since made this vibrant city my home. I hold a PhD and MSc from National University of Singapore, in which I've involved in research related to urban environments and microclimate. And currently, I'm a senior research fellow at the Department of Building, NUS. So in this role, I also serve as the co-principal investigator or co-PI for this project, CoolNUS-BEAM project. Then prior to this, I was a senior research fellow at the Urban Analytics Lab, led by Philip Legiecki at NUS. I was working on urban data science and geospatial analytics, contributing to research that supports sustainable urban development, digital twins, and also smart city initiative. And most of my studies so far has been around urban geometry, urban heat island, microclimate, and also outdoor thermal comfort, especially on enhancing the comfort of outdoor spaces through better urban designs. So to get started with how this project has come to alive is due to NUS has this campus sustainability roadmap for 2030, which spells out long-term approach and commitment towards being a carbon neutral, climate resilient, zero waste, and biophilic campus. So furthermore, the university gives annual updates on our campus sustainability performance. And our group particularly involved in the CoolNUS initiative, which deals on how to improve thermal comfort and support the tree planting program. So the purpose of this BEAM project is to support CoolNUS campaign, which comprises campus-wide weather monitoring and simulation to understand the local microclimate condition, investigate heat island impact, identify and apply mitigation strategies to improve outdoor thermal comfort condition. So the BEAM team comprises the main key people with Prof. Wong Yuk Hien, who is an expert in heat island studies, and we collaborate with me as a co-PI and also Clayton Miller and Phil Brzezinski to add up the expertise from the artificial intelligence and also geospatial. Supported by bright minds of researchers and PhD students among our team and also the campus infrastructure. We also, at the moment, we are reaching out for collaborators, both internal and external, to be involved in this initiative. Because we also want to promote horizontal collaboration among researchers to make use both of our data and digital twin. We also just kickstarted the website, which you can access from coolnus-beam.sg. It's an ongoing platform, so it's still in development, but you are able to go through our digital twin platform, so you can see how our sensors are located and what kind of data that has been collected. Okay, so BEAM refers to our research methodology. So it stands for baselining. We begin by analyzing historical data to establish a benchmark, providing a foundation for assessing ongoing and future plans. Then evaluating, we evaluate the baseline results to identify hotspots or areas with high thermal conditions or discomfort. enabling targeted and effective mitigation strategies. Then we go with action. We test various mitigation strategies at a small scale, assessing their effectiveness and impact on thermal comfort and other key variables. Then lastly, the monitoring. This is the critical component of the BEAM, involving continuous microclimate monitoring across the NUS area by deploying an extensive network of sensors. Then we collect valuable microclimate data that is essential for assessing the campus environment in the past, present, and future. This long-term data collection allows us to track changes, validate the effectiveness of our strategies, and make informed decisions to enhance thermal comfort and sustainability on campus. And everything, we try to encapsulate everything and convey our findings and our data visualization through the digital twin, which I will do some showcase for you later on. This is so for the past 1 year we have been working on installing the weather stations. So we have 40 weather stations combined in our NUS campus at the ground and roof levels. We also installed infrared thermal cameras at the rooftops, and we also have 3 MET towers. Each of the MET tower is a 12-meter high with comprising 4 different thermal sensors at 4 different heights. And we put everything in digital twin platform that we developed to facilitate near real-time weather data visualization and presenting simulation and study findings. So this is a screenshot of what kind of data that we are collecting. I will showcase to you in my demo at the end of the slides. So the data that currently we are displaying is the weather station that comprises the air temperature, the solar radiation, the humidity, and also the wind rows comprises the wind direction and also the wind speed. And the infrared thermal camera is a time series data collection of the different section of the NUS campus, and the meteorological tower that shows the air temperature profile within this 12-meter high. So with all those data collection, we also leveraging on our previous data collection across NUS with a lesser number of sensors. So we work with the historical weather data assessment. Then we develop the urban morphological analysis in order to assess the outer thermal comfort. And from all this historical data, we establish the baseline condition. So all of these are based on the ground truth data collection. And then from here, we conducted interpolation where we developed the climatic maps in monthly climatic maps based on our previous data collection in order to identify where are the hotspots across our campuses. We also correlate the data collection that we get from the weather stations into the urban morphological factors assessment, in which we try to see at each of the weather station location what are the components that or the variables that affecting this microclimate. By using on-site survey and GIS geospatial data, we are able to quantify the following variables, such as the building footprint percentage within this 50-meter radius of each of the weather station, and also the amount of the pavement or roads, pavement, and also sidewalk. And also we also calculating the impact of the shading from the greenery, calculating the sky view factor, the shading from the building, and also the green plot ratio. Green plot ratio. Yeah. So the green plot ratio is a measurement of how much of the greenery the greenery density at certain location. Apart from this on-spot data assessment, we also try to conduct something like interpolating this data points with the 2D, a combination of 2D and 3D data sets, in which we combine different layers of geospatial data, buildings, and also greeneries. We also conducting simulation of the shading due to these two elements. Then from there, we develop the climatic maps. After we conducted the climatic maps and we identify where are the problematic areas, we try to come up with mitigation. So we're not just like doing evaluation, but we also try to apply this realistic mitigation options, either passive or active. So passive means that we try to introduce let's say cool paint on the facade or pavement, green wall, or we improve the walkability by shadow walkway, or we try to minimize the hard pavement on the car park spaces, let's say using more permeable pavement. And also we adding up the trees by a very ambitious tree planting scheme. And we also try to minimize the heat gain through the glazing through the solar film. So adding water features, or we also try to implement a combination between solar panel and roof garden. And we also try to introduce more void decks in some of the buildings. And also we try to see whether we can install some of the active measurements, such as more mechanical fans, even drainage system, or on-spot active cooling devices. And of course, these are based on depends on which location and whether they are feasible. And also we are looking into other options that through specific studies that is currently being doing by our collaborators. So we, based on our historical data, this is a data collected from 2019, 2020. So this from the previous data collection, not from the new weather stations, in which we develop climatic mappings monthly. From here, we can see that there are some hotspots and cool spots that we can identify throughout the campus, but we can also see the impact of different seasons during the dry and hot seasons, which is usually happens in the inter-monsoon period. And also you can see that in December, January are our wet season, rainy seasons. So usually we can see that from July to September, usually are the hottest period, except that last year, apparently April happens to be one of our driest month. So yeah, we hope that with the new sensors installed, we can get a better reading on how this microclimate profile each year can be identified. So based on the hotspot identification, we try to zoom into these 4 locations and how we can try to apply mitigation strategies at these 4 locations. So we haven't got a full concrete long-term plan for some of these locations. So we just kickstarted to do some test bed of the mitigation strategies, such as the cool paint and solar film at one of the locations. So we have like 4 quite distinctive areas. So we have a sports court and field. We have a engineering faculty. We have a science and medicine blocks, and we also have a student residence at the Prince George Park. So apparently when we did a closer look into the hotspot assessment, we conducted, when we look at the data set, so usually it's because due by either lack of greenery, tight urban canyons, very low wind speed, and also a large pavement that becomes a heat sink, such as the hardcore pavements for the sports activity like basketball or tennis, and also open car parks. So from here, our team worked with the campus infrastructure, conducting assessment on what are the appropriate mitigation strategies that can be implemented. So for the tennis courts and we have like several, we have a big area of the basketball courts, tennis courts. Usually, so all of these areas, we still have the typical paint. So we are conducting studies on whether we want to use a cool paint that specifically can be used for sports activity. So this one is currently under a proposed action, in which should be realized by next year. In which we also did some study. If we compare the hard court, the basketball court, with the real turf, we can see that by looking into the surface temperature, they can be about 10 degrees hotter than the real turf. So primarily due to the extensive solar exposure and low solar reflectance. indicating a high absorption of solar heat. So in engineering blocks, so we have identified those open spaces and also the car parks. The markup. We look at them how we can apply the full pavement at these open spaces. The main factor is the solar reflectance or SR. So this solar reflectance is the main characteristic of the full pane. So it represents a ratio of solar energy reflected by a surface to the total incident solar energy. It varies from like usually like 0.1 for artificial turf, 0.15 for basketball court, and maybe 0.38 for real turf. So you can see that if we look at the surface temperature, it can be as high as 57 degrees during the daytime. So we currently we have applied the cool pavement. We painted this area. We have selected two areas where we want to do some pilot study comparing the cool paint and also another one as another area nearby as a control side by side. We want to see the impact in the short term. What is the during the daytime, during the clear day, what is the surface temperature comparison between these two lanes. Currently, the measurement is still ongoing, so we hope to get some results in the next few weeks. Then we also selected one building. It happens to be part of the campaign for the full paint. So it's also just nice, just in time for the campus infrastructure to do repainting of these older buildings. And we propose that these buildings to be painted with the full paint. So we have one engineering building that will be that has undergone the full paint application. And for the glazing and the windows, we apply solar film. We collaborate with the 3M for supplying us the solar film. From the initial study, it shows that yes, the solar film can reduce the incoming solar radiation, which means that it can affect the cooling load as well. Means that we can reduce the heat gain and reduce the cooling load. Currently, we are also doing measurement using the thermal camera. The thermal camera can assess the surface temperature across the time, and we also install thermal comfort stations on this roof deck because we understand that the impact of the full paint. The idea is that to reflect the solar radiation. Means that the solar radiation have to go somewhere else. So we also try to see what is the amount of the reflective solar radiation and whether this will impact the temperature during daytime and nighttime as well. Another location is the PGPR, as I mentioned before, is student residence. So here the problem is a bit different from the others. Is this area has been quite famous for a hotspot in NUS because due to the very tightly dense building arrangement, and also because of the nature of the curve shape of the building. So means that at most of if we do some solar radiation annually, if we do annual solar installation simulation, we can see that some of the building blocks are constantly exposed to the sun. So it means that that's why we have received some feedbacks from the students, especially of those students that are staying in the units without the aircon, because we can choose the option whether we want to use the aircon or non-aircon units. So they are have some feedbacks that during the daytime and also even nighttime, they felt discomfort due to the either humidity or the hot weather. At the moment, we are conducting Amphimet study to zoom into some of these units and also conducting detailed energy simulation to assess the impact of this high solar radiation, and we try to see whether we can install some solar shading at some of the identified units or blocks. So we can see that the problem at this area is that, although the first of all, because of the layout of the buildings and amount of roads and pavement, increases the temperature, become a heat sink. And another problem is that the wind speed is quite low. So you can see that at 1.5 meter high, the wind speed within this PGP area is quite low, almost non-existent. And we can see that the mean radiant temperature at the open spaces and between the pockets of the buildings is also quite high. This one adding up the problem that there's not much space for the campus infrastructure to add more trees. And also because most of the open spaces are like a roof deck, because underneath there's a parking is purpose for the parking spots. So means that they are unable to add the trees due to the roots, and also they cannot add more load to the roof decks. So some of the potential mitigation that we try to look into is that whether we can adding up some green roof at two of the main canteen blocks where they have a flat roof, and at the moment there's has been used for other equipment. And we also try to change this big glass canopy for the drop-off area. Whether we want to add solar panel if the load permits, or we want to add solar film. We add solar film on the top of it. And we also try to minimize the pavement area to add more turfing, and also this open space in the middle. Initially they wanted to become like a plaza for students to mingle, but due to the nature of its openness, actually not many students actually do their mingle or their gathering at this location. So we try to see whether we can discard the water feature into a community garden with some shades. And also we try to apply the cool paint for the sports courts. So those are the things that we have identified through our exercise of like doing the baselining, we do evaluating, and also we are doing actions. We also try to support the tree planting campaign. So the work scope is that we actually do not have a complete database of our own greenery. So I think the first thing that we try to do is that we want to compile a very detailed database in which we try to develop something like an inventory system in which we can see what is the tree baseline condition, and then we can also help the tree planting facing. Where are the strategic location where we can put the trees to put more shades, and also to help with the thermal comfort issue. Then we can also do a benchmark tree impact study, like past, present, and future. Then we can also do some scheduling for the tree maintenance with this greenery inventory system. So what we have done is that we have so this is our deliverable, in which we have developed not just a point shape file of the greenery database that have the species, the dimension, even we collected the gut size and also the canopy size. We also do some 3D modeling, in which the 3D models referring to the shape of the trees, as well with the help of some from different sources. This is in line with how we want to use greenery to improve our outdoor thermal comfort. So the first step is that we want to digitizing the campus tree inventory. So we are working with other group. It's called the Center for Nature-Based Climate Solution, CNCS, with the campus infrastructure. So we do from different layers of we do from different scale, very scale. So we go from ground until using the satellite imagery to see the progress of the tree planting program. So the idea is that from 2020 to 2030, the NUS plans to plant about 100,000 trees. So means that about 10,000 trees annually. So I mentioned that we try to develop this greenery database using several means. So first one, we also conducted a campus-wide 3D scanning using LiDAR, in which we are able to collect a good amount of data set, not just from the buildings, the roads, but also the 3 points. So from the point cloud data, we are able to capture those, especially those shrubs area underneath the trees, which usually are blocked if we using the satellite imagery. So we have like tree layer, we have turf and shrub layer, and we also have a forest layer. So if we combine together, we have a pretty nice greenery digital model in which that we hope that we can also use this for our microclimate simulation, and also to for us to conduct the campus-wide urban ventilation studies. So from the greenery data set, we also look into the past data. So we look into historical satellite maps using NDVI. We can see that throughout the years, NUS as a whole, the portion of the non-greenery with the greenery has not been changed a lot. Eventually, if to be precise, from 2019 to 2024, we have added about 1% plus of the greenery area. And to bear in mind, between this period, we also have new developments in which we have to open up some lands. And 1% of this area is about 1.8 hectares, if I'm not wrong. So this information allows for separation of using NDVI. It facilitates an understanding of vegetation density and the evaluation of changes in plant growth as well. So by comparing NDVI data from different years, changes in greenery extension can be evaluated. So these changes will be analyzed in conjunction with the weather station data. So if we look at the greenery portion, about 60%, if we compare from 2019 to 2024, so the greenery portion, if we're using the satellite imagery, comprises the open grass or shrubs area and also the tree canopy area. So we can see that from 2019 to 2024, the significant change is that most of the green spaces are already being covered by the tree canopy. So it shows that we already almost halfway through the tree planting program. Although not all trees are when we put the new trees are in the mature state, but we can see that there are some of the old trees are growing, and also the new half mature trees are planted, also adding up to the tree canopy area. So for the new map is this new map is the calculation that use the 2024 NDVI minus the 2019 NDVI value, shows the change of greenery. So the positive high value is the new tree planting, and the positive low value is the growth or healthy situation for the greenery. So it means that they are growing. And the negative value, which is the purple, means the decreased green area, which has transformed into the new building or new development. So we can see where are the growing trees and where are the new trees. And for the latest one that we are trying to work is that with all those information from the weather stations data as a boundary condition, with the new 3D model of the trees and also other geospatial layers, we are working with the Kajima Research Institute. So we try to study the urban ventilation of the campus, especially on the understanding the impact of the sea breeze on NUS campus. So this is the NUS area. So this is the sea, mostly based on the weather station data. We understand that the sea breeze mostly coming from the north and northeast. And the interesting thing is that this port will be moved out to other locations. So means that we will also want to study the impact of this new development at this area to our campus as well. We also did our previously we also did our urban ventilation study, but last time we didn't have the full 3D of full information of the greenery and the trees, so we didn't include that in our previous study. So we hope that we can have a more complete assessment using our current data set. So so I want to show on what we have installed and what we have developed for the digital twin. Okay. Sorry, I need to share that other screen. Okay. So yeah, so if you go to the website, so if you click on this BEAM DT, it will brings you to this our digital twin. So as I mentioned before, so I will show you step by step on our sensing our monitoring campaign. So this is our 40 weather stations across the campus. The pink one is the roof weather stations. So you can see that for each of the weather station, we collected the 4 main variables. So this chart shows the last 30 days of the data collection. So this is initially our weather station collecting our weather station are currently collecting data every 1 minute interval. Then we transform them into hourly data to be showcased here. We have air temperature, we have the solar irradiation, we have the wind direction and wind speed, we have the humidity. This one is a rain gauge meter. I think from all the 40 weather stations, we have 3 rain gauge to indicate where are the rainy days as well. Another thing that we try to implement here, maybe a bit of AI element here as well, is that we do computational computing vision segmentation. So this is the 360 panorama image of the center of the weather station, in which we do image segmentation, where we try to put a label on how much is the pixel area for the sky. We have 6 elements here. Actually, they have like 19 different categories, but we just select 6 that that is meaningful for our study. So we have the vegetation, we have the sidewalk, we have the building, we have the roads, and we have the terrain. So we can also try to use this as additional information on how to explain why the temperature profile or the weather profile from one location differs to another. So in this case, let's say if we choose this one is near this is the hotspot, the sports court area. Then if we choose, let's say, weather station from a deep canyon between 2 buildings, then we can see the temperature profile already different. And this is mostly due to the lack of the solar radiation at this location number 3. And it's also impacting other areas. Then we can see that from these 2 locations, that the SVI, the street view imagery from our panorama image and with the segmentation can also explain the composition, that you can see that this sky portion is smaller than this one. The sky view factor means that this one is more like obstructed than this location. And we can also do this comparison with the other location throughout these weather stations across the campus. Also an ongoing work, we have 6 thermal cameras. So the idea, we try to capture as many angles of the campus. So let's say for this one, because we are studying the E1A building, the one that currently we are applying the full paint. So we can choose on which day that we want to see the data output. And then from here, we can also try to compare the data with the nearby rooftop weather data from the weather station to see what is the, let's say, the solar radiation value. So it might explain the high surface temperature at the facade at certain timings as well. So we have collected the data since, I think we have collected most of the data since April. So we have like 4 good months of the data. And you can see that for the, I think I didn't mention that for the weather station data, it's not like real-time data, but you can see that it's almost a near real-time. When we develop the system and also the platform, there's some time lag for the sensors to be collected into the server. But I feel that at this rate, we are quite happy with our data collection with this interval rate. So the last data collector was about actually 15 minutes ago. So actually, it's not that bad. I mentioned that from this is the climatic maps. So this one is not based from the 40 weather station, but this one is from 2019. So how we try to see how we can map out where are the hotspots and also where are the cold spots and where are the potential locations that we can try to improve by adding more trees, or we can try to apply other intervention. Another thing that we did that we try to play around is that because we are focusing on the walkability and also auto thermal comfort, we also conducting this so-called thermal walk. So thermal walk is the campaign that we did combining several studies. So initially we asked one person, actually the last time there was like 3 people walking together. So one person is holding a GoPro Max. The GoPro Max is used to capture this 360 panorama while we walk. We record a video, then we do a segmentation later on. And one person is holding a mobile weather station, and another person, and the same person also wearing a wearing an Apple Watch equipped with the Cozy app. So what it does is that when we do the thermal walk, we just want to provide something like a prototype of a study where we can collect not just the dynamic data from the weather and also the physiometric individual physiometric, but also the static element, which is the surrounding condition of the urban morphology. So you can see that for those areas with the open spaces, we can see that it was nicely identified by using the segmentation. You can see that at this area, at the running track, it's very open. So you can see that the portion of the sky is very high, and it's also being supported by the data where it has very high global horizontal irradiance. And every 50 meters, as part of the thermal comfort study, using the Apple Watch with the Cozy app, we also ask several questions as part of the thermal comfort survey. At the same time, the Apple Watch also collecting data such as like oxygen saturation or heart rate and maybe elevations. There are a lot of that data has been collected as well during this walk. The idea is that we try to map out those walking route. For instance, we can study where are the routes that has been heavily used by the students or the staff to mobilize from one location to another. We are also working with the because the NUS is quite hilly, so to walk from one location to another can be quite challenging. There's also another ongoing study on how to make the shuttle bus becoming more efficient. It appears that some bus shuttle route, right? Some people rather than walk from point A to point B, they rather just to take the shuttle bus for one stop, then they will alight at the next one. So we try to improve the loading of the buses as well, and how to ask people to walk for those shorter destinations. So this is a prototype of the thermal walk that we have developed at the moment. The next step is that we want to identify where are the main pedestrian walk, and we hope that we can use more like improvements at those sidewalks. Hopefully people can go out and walk more. Yeah, so that's for the demo of the digital twin from the website. You can go in and you can try to play around and see different type of data sets. So yeah, so that's what I have at the moment. I hope that I don't have much of the artificial intelligence components. The idea is that we have like this big data set, not just from our microclimate data collection, but we also have quite nice geospatial data. We also have like satellite imagery. Yeah, so the idea is that you know that we usually before for the key element for the machine learning and the AI that you need like good data input for training. So we hope that I think Miguel is here. I'm working with Miguel as well. How we can leverage, let's say, if we want to study cooling load of not just a building but also a whole district, using our weather station data as a data input. So means that we already identified the local context of this area and we feed them into the energy modeling, and we hope that we can develop something like what Miguel has mentioned last time as a surrogate model, which we can use for our future, let's say future master plan, or if you want to enhance the performance some of the buildings or improve some of the indoor quality as well. Yeah, so I hope that using this platform, we can do some discussions or any ideas that can be motivation for us to do more collaboration. So yeah, so Ivan, that's all from me. So thank you for the time given. Yeah.
Yeah, thank you very much for explaining such a first solid microclimate and building sustainability project. And yes, one of the objectives for the discussion seminar is actually, machine learning requires good data, and there are some good data like how the AI or the machine learning experts can give some of the insights or like bring some potential collaborations together. So yeah, thank you again, and perhaps I open the floor. If you have any questions or any things that you would like to discuss or related to building sustainability or something about the data, about the project, how to collaborate, feel free to unmute yourself and ask Marcel and Miguel.
Mm-hmm.
And I will stop recording.